In harmonic motion and simple harmonic motion, as we would expect, mechanical energy is conserved as long as we ignore any dissipative forces. So therefore, the potential plus the kinetic at any given point would give us the total energy. So with a simple harmonic oscillator, our displacement is equal to the amplitude times the cosine of the phase angle. So therefore, potential energy would be 1/2 k times that value squared. And also, kinetic energy would be dependent upon the speed, and the speed would be 1/2 mass times, or the kinetic energy would be 1/2 mass times the speed squared, so we'll take 1/2 mass times our speed equation for a simple harmonic oscillator squared. Now these equations are kind of awkward to look at and to use, but if we address them at maximums and minimums, they become much easier to use. For example, at the point of maximum displacement, the velocity of the object will be 0. And therefore, if the velocity of the object is 0, all of the energy must be potential. And since we're at the amplitude, our phase angle would be 1, would come out to be 1, and therefore the equation for total energy would be 1/2 k times amplitude squared. This again would be at the point of maximum displacement, okay, when our cosine of our phase angle is 1, comes out to be 1. We can also look at the point of minimum displacement, in which all of our energy would be kinetic, and find the total energy that way as well. Here are a couple of sample problems to take a look at and to try and work out before coming to class. You have an oscillating block spring system with a mechanical energy of 1.18 joules, an amplitude of 9.84 centimeters, and a maximum speed of 122 meters per second. So see from that information if you can find the force constant of the spring, the mass of the block, and the frequency of oscillation. And it's a very similar type problem for the second problem here. And again, attempt those problems before you come back to class and bring any questions you have on those. Now we're going to look at 3 very specific applications of a simple harmonic oscillator. The first being what we would call a torsional oscillator. If we suspended a heavy disc from a wire or a string and rotated it out, the torsion in the string, which is the twist in the string, would cause it, of course, to unrotate back to equilibrium and then over-rotate again. And neglecting any dissipational forces, this would continue to occur forever. The restoring force here is really a restoring torque. It is, of course, working opposite of the displacement, so the restoring torque would be minus k theta, still following Hooke's law. In this case, we can derive this equation, but we just need to simply know it. And what it comes out to be is that the period of a torsional oscillator will be 2 pi square root of I, the moment of inertia of the disk, divided by K. K would refer to the torsional force constant of the wire from which the disk is suspended. A second example that we will identify is the simple pendulum, where all of the mass is located in the pendulum bob. In this case, the restoring torque is due to gravity. So as long as we are talking about relatively small displacement angles, then the restoring torque is indeed going to be simply the weight force. And our period will be defined as 2 pi square root L over G. Now if we're talking about larger angles of displacement, then we have to factor in the sine of theta, so we would get the period would equal 2 pi square root of L sine of theta over G. But for the most part, if we're talking about a simple pendulum, we're assuming that we have a relatively small initial displacement. The third kind of simple harmonic motion we're going to look at is the physical pendulum. This would be like, for example, not a simple pendulum. For example, if you were to oscillate a baseball bat or some such figure as this thing that looks like a potato or some darn thing. The period of this torsional pendulum, physical pendulum, would be 2 pi square root moment of inertia divided by mgh. mg obviously is the weight of the object. H, by definition, is the distance from the center of mass to the actual pivot point of the object. We will look at a physical pendulum and a simple pendulum quite a bit in this course, so these are two equations we definitely want to be familiar with. Again, some sample problems to look at and to examine before coming back to class. Again, bring any questions you would have on these problems with you to class so that we can work them